This is Tiina Reponen from University of Cincinnati, and I'm chairing this last session today. So far we have had quite extensive information packages about sources of indoor particles, transport and dynamics and exposure, and now we will be hearing how to mitigate, how to intervene, how can we reduce the exposures. First speaker is Bill Fisk, senior scientist from Lawrence Berkeley National Laboratory, and I just heard that he's actually recently retired, but he's still working. So happy to have you here.
Hey, thank you very much. I really appreciate the opportunity to talk. I was asked to talk about particle mitigation, which is a broad subject, and then Bill Nazaroff came out and said, we want deep discussions, not sort of broad discussions. And I sort of put those two together and punted, I guess, and I'm going to really focus mostly on filtration as a mitigation technique. And there's a few things just up front. I hope you can remember about filtration, or I want to make this point. Filtration can be very effective in reducing indoor levels of particles. However, the current practices that we use in filtration are often relatively ineffective, and it wouldn't cost us much. It wouldn't be that hard. We have the technology to do a much better job today. So those are the real bottom line there. But a little context. Let's see, which is my pointer here? Okay, so filtration is one of the usual portfolio of techniques to mitigate, and of course reducing the indoor sources should be your first priority always, but at the individual level, only at the sort of societal level can you reduce the sources of outdoor particles. So it has some limitations in terms of what you can do, but obviously it's something you need to do first and foremost. We just had this discussion about outdoor air ventilation. It can remove the indoor generated particles. It brings in outdoor particles. My view is it's not a very good particle mitigation technique, and filtration is far better because it doesn't have that disadvantage. And there's filtration, which I'll talk about, and then there's other techniques to enhance the particle deposition on indoor surfaces, like using ion generators and increasing air movement. I'm not going to talk about those, but there may be some potential there. With ion generators, I'm a little worried about how they also affect the particle deposition in the respiratory tract. And then within filtration, there's a host of technologies. I'm not sure this is my final version here, but it'll work. Host of technologies, and I'm going to focus on the sort of the dominant technology out there today, which is to use fibrous filters or stretched membrane type filter media. But there's electrostatic techniques, combination techniques, and I think Brad will talk about sort of using the building envelope as a filter, or a tight building envelope as a filter. So I think all of these have potential, but given time constraints, I'm going to focus on the first. Performance factors for filters. There's really a host of them. I'm not going to go through all these, but there's a set of factors that affect the particle removal, a set of factors that affect the energy and the cost of filtration, and then there's some other factors like reliability and pollutant production from the filters. And a few of these, I think, people don't pay enough attention to, so I want to highlight them. One is the sort of the duration of the airflow. Brent, I think, talked about this, and that can be very low in a HVAC system in a home. Another is, where is the filter located relative? Is it filtering the incoming outside air, recirculated air, a combination of two? Where is it relative to the sources of pollutants? Where is it relative to the people? Important factor, almost never focused on. And how much does it cost? Because I think that's a big factor that drives whether people are going to use filtration. Okay, so filtration can be really effective, but it's not always really effective. And this is a figure that really communicates a lot of information based on a study of particle removal techniques in 9 classrooms in Southern California. So your axis, vertical axis here is the removal effectiveness. It's essentially the reduction indoors relative to outdoors. And then these are different classes of particles: black carbon, ultrafines, 0.3 to 0.25, 0.3 to 2.5, PM 2.5 mass, and PM 10 mass. And let's just focus on 3 bars. The leftmost bar is sort of the baseline school where we've got a low efficiency filter, but at least we've got the HVAC running continuously. And these are the removal effectiveness values you can see here. The next bar over is where they've added a high efficiency standalone filter in the space. And I estimated that it was processing about 2 to 2.5 indoor volumes per hour. And you can see the removal effectiveness jumps up quite a bit. And you can see that's the case for all the different categories of particles here. And then the rightmost bar in each group is where you replace that low efficiency filter in the HVAC system with a MERV 16 filter, a much more efficient product. And again, you see much bigger improvements in removal effectiveness. So filtration here can be quite effective. Baseline filtration is not that effective. And it's effective for a broad range of particle types. Also, filtration can be quite effective for nanoparticles. This is a controlled laboratory study, and this is the particle penetration, or 1 minus the efficiency in the vertical axis. And each of these curves here is a different filter type. And first of all, just look at the axis values. The penetration factors range from about 20% down to a fraction of a percent. So for these nanoparticles, the filters are removing them quite effectively. And that's even for filters that have quite a substantial penetration at 0.3 microns. So filters can work well for these nanoparticles. It doesn't mean your run-of-the-mill see-through furnace filter works well for nanoparticles, but filtration can work for nanoparticles. However, what do we require today in standards? Very low efficiency filters, for example, in the ASHRAE standards, about a MERV 6, unless we have high outdoor PM levels. And here's an example curve of the particle removal efficiency versus size for a MERV 6 filter. For most of the size range, it's below 20%. And for a lot of these particles, it's below 10%. So the filters that we're commonly using have a very low efficiency for particles in sort of the most interesting size range. Also, what do we do today in homes is we put those low efficiency filters in our HVAC system that runs intermittently. And you can do this very simple calculation to show that you're not getting much particle removal for PM 2.5 here. If you look at more than half the homes have a MERV 6 or lower filter, given the small amount of data we have. Efficiency is low. Here's a typical flow rate per unit volume in a duty cycle. And the total removal rate on a volume normalized basis is less than 0.1 per hour. So those filters are not really bringing us a lot of benefit, but that's what we do today. Charged fiber filters, Jeff, you touched on this. There's a lot of filters, big part of the market that has embedded charged fibers, and that can increase at least the initial removal efficiency. But the data suggests that for some particle types, you see these rapid drops in efficiency. Here's initial efficiency of a filter, and after 20 cigarettes, the big drop in efficiency. Here's the initial efficiency for diesel particles, and as the filter loads, efficiency is dropping. And this filter is far from used up. Its pressure drop hasn't increased that much, but its efficiency has dropped dramatically. And however, for something like Arizona road dust here, we don't see the efficiency drop. And I haven't looked real hard, but I don't think we really fully understand the physics that's behind this process. Another trend in the field is to use nanofiber media and filters. And as the filtration industry uses the term, a nanofiber is less than 0.5 microns in diameter, whereas a typical filter is a micron or so, or tens of microns or so in the fiber diameter. And usually the nanofiber filters are composites where they may have layers of micron-sized fibers and layers of nano-sized fibers in that filter. But this is a trend, and they can be there's experimental data showing they can be very effective for the small particles, but there's a little bit of data now suggesting also that you can get a higher ratio of particle removal efficiency to pressure drop with these nanofiber filters. So I think they offer some potential that way. I think this is not the main way to improve filter performance. There's other ways, but this can help us. Another point I want to make is that the sort of energy used to remove particles by filtration varies dramatically depending on the system one is using. So here I'm comparing an HVAC system in a home with a low efficiency filter, and we've put in some typical numbers, and we've estimated that the electricity to run the fans cost about $17 for every gram of PM removed. You go up to, that's if you're running this thing continuously to get your particles removed. So you run this thing continuously, but you put a higher efficiency filter, you bring that down to about $7 per gram of PM removed. But if you have a high efficiency standalone unit, okay, two things happen. The efficiency of moving air is better, and the efficiency of particle removal is better because they use better particles. So for every unit of air moved, you get more particles removed. Bring this down to about $1 per gram of PM removed. So there's a dramatic difference in the energy cost depending on how you do the filtration. One of the reasons people don't want to use better filters is they think that they're going to increase the energy costs and the airflow resistance, and it's prohibitive. But the data really doesn't bear that out. You can use deeper filters and more plating, and you can keep the airflow resistance down. What happens is that the filter cost itself, the media cost, does increase. But I'm going to argue that that increase isn't so high. First of all, what happens in a residential situation, this is by my colleague Ian Walker, who said that the fan energy in a home changes by about 1% or less. You use high efficiency MERV 10 to 13 versus MERV 6 filters. So not a very big effect there. And here's a nice life cycle cost comparison of filters with different ratings, accounting for all the factors. And I've converted those to a per person cost. And so we can see the range is $7 to $11 for the very low efficiency filter, $19 to $35. So we're talking about a fraction of a dollar to maybe $3 per person per month to get a lot better filtration in our commercial buildings. And the incremental cost of getting better filtration is about half of that amount. So it's not a very expensive process, even when you account for all the costs. Okay, a couple of years ago, I had published a review of the literature on the health benefits of filtration. And I want to sort of give you two main conclusions. The first has to do with using filters in homes to reduce allergy and asthma outcomes. And there's a lot of good quality studies today, controlled studies with placebo filtration versus real filtration in homes, looking at allergy and asthma outcomes with both self-reported and objective outcomes. Does it work? The answer is, unfortunately, we don't see a lot of benefit. We do see some evidence of benefit, predominantly just in the homes would have pretty strong allergen sources. And even in those situations, we see moderate reductions in the health outcomes, and a lot of the health outcomes are not improved. So it's not the solution to these problems. What looks like its greatest potential based on the published literature is the reduction in the morbidity and mortality that we find associated with outdoor particles when we use better filtration to reduce the indoor concentrations. And several studies have looked at that. It's a lot of unknowns in terms of whether those risk factors that they're using for outside apply indoors. But to the extent that they do, this is quite effective, and that the health benefits far exceed the cost of those interventions. Skip that. I want to talk a little bit about some of the challenges. I'm not going to cover all these, but I think given that we have good technology and it's not that expensive to use, but it's not being used, I think one of our challenges is really doing a better job of quantifying, demonstrating, and communicating, the benefits of filtration today. Something we can try to do better today. I think I'd like to see us try to encourage those involved in the standards process to up the minimum requirements. I think one of the challenges is for allergens or locally resuspended particles. I suspect that filters don't work particularly well for allergies and asthma because it's not, the exposure mechanism may be substantially due to local resuspension of allergens, and filtration isn't very effective. So we need better ways to mitigate those exposures, or other ways to mitigate those exposures. We have many very expensive products people are spending hundreds of dollars for. They put in their homes, and they're worthless products. And so we're not communicating well enough to people so they make good decisions. So I think that's an important need. Two other points that aren't on here. There's a move toward natural ventilation in commercial buildings. There's a lot of reasons to go toward natural ventilation in commercial buildings, but that increases the exposures to outdoor particles. So are there ways that we can mitigate the adverse particle exposures and ozone exposures in those naturally ventilated buildings? And the other issue I wanted to mention is we want to get a better understanding of the health risks of outdoor particles and indoor generated particles. And we can use filtration as a tool to sort of differentially affect our exposures to outdoor source particles and indoor particles. And I think that could be a tool that we could use in future health studies to get a better handle on that question. I think that's it. So briefly, filtration can be very effective, PM 2.5 and ultrafines. We can do a better job today with minimal increase in energy costs and moderate increase in total costs. But typical practice today is not very effective. These high efficiency standalone filters can remove PM using a lot less energy than home HVAC filters. And it looks like the largest health benefits, at least given what we know today, are probably associated with reducing exposures to outdoor PM, not related to the allergy and asthma problem. So thank you.